Okay, so welcome to this lecture. So in the previous lecture we had defined connectedness, and today we will continue with that topic, and today we are going to define path components of X. I'm sorry, not the path components, the connected components. So let X be a topological space. And we put an equivalence relation. Okay, let's put a relation on the points of X as follows. We say that X is equivalent to Y if there is a connected subset T contained in X such that X comma Y are in T. So let us check that this is an equivalence relation. That this defines an equivalence relation. On X. So there are three things which we need to check. First, we need to check that X is equivalent to X for all X and X. Right? This is clear because by taking T equal to just the singleton set X. Any singleton set X is connected because for a set to be disconnected, it has to have at least 2 points, right? Because we cannot write the singleton set as a disjoint union of non-empty open subsets. In fact, as a disjoint union of non-empty subsets. So the second point we need to check is if X is equivalent to Y, then Y is equivalent to X, right? This is also clear as if T is a connected subset which contains X comma Y, then it obviously contains Y and X again. So Y is equivalent to X. 3. If X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. Right? To show this, recall that in the previous lecture we had proved that if T1 and T2 are connected subsets of X such that T1 intersection T2 is non-empty, right? Then the union T1 union 2 is non-empty, is connected. Right. Now since X is equivalent to Y, there exists connected subset T1 such that X comma Y are in T1. Right. Similarly, since Y is equivalent to Z, there is connected subset T2 such that Y comma Z belong to T2, right? So then Y is in the intersection and so it's not empty, and thus T1 union T2 is connected. and contains x and z, right? So thus x is equivalent to z, right? So this shows that the sim is an equivalence relation. Okay. Now every time we have an equivalence relation on a set X, we can decompose it into equivalence classes. So this equivalence relation breaks X into a disjoint union of equivalence classes, right? So we can write X as a disjoint union of Xi's. I is in some index set I. Yeah. So and each Xi is the equivalence class of some X. Right, and X is equivalent to Y if and only if X comma Y belong to the same Xi, right? Okay, so we have this following proposition. Which has, let's say, 3 parts. So every connected subspace of X is contained in Xi for some I. Right. Given any connected subspace of X, it is going to be contained in one of the Xi's. So the second part is each Xi is connected. Right. So every connected subspace is contained in some Xi, and each of these Xi's is connected. So therefore, these two will imply that Xi's are maximally connected, are maximal connected subsets. Of X. And the third point is each Xi is closed in X. Okay. So let us prove this proposition. So let T be connected subspace of X. Right. So assume that T intersection Xi is not empty and T intersection Xj is not empty. So we will prove the first point by contradiction. So let's assume that a connected subspace meets two Xi's. So it meets Xi and Xj, where I is not equal to j, right? So let T comma S belong to T, right? So then by the definition of the equivalence relation, so then T is equivalent to S, right? As T is connected and it contains both T and S. I'm sorry, so I should have written let T be in T intersection Xi and S be in T intersection Xj, right? Then as S comma T are in T, this implies S is equivalent to T, right? But then this implies that the equivalence class of T is the same, which is Xi, is equal to the equivalence class of S, which is Xj, right? and this is a contradiction. Because xi is not equal to xj. So therefore, given any connected subspace, it can be contained only in one xi. Okay. Next, let us prove, so this proves 1. Next, let us prove 2. So let xi be an equivalence class and let x be in xi. Okay, so we fix this point x. Okay, then for any y in xi, yeah, since x and y both of them are in xi, as x is equivalent to y, there is a connected subspace T sub y contained in x such that x. Right, I'm just using the definition of the equivalence relation such that x and y belong to T sub y. Okay. So clearly, from this part 1, yeah, from point 1, it follows that Ty is contained in xi, right? So thus we can write xi as a union over all these y in xi T sub y. Okay. Right. So this inclusion is obvious. This inclusion is obvious because for each y in xi, the subset T sub y that is contained in xi, and therefore when we take a union, it's going to be contained in xi. Yeah? And conversely, for the other inclusion, T sub y, for every y in xi, T sub y contains y, right? So therefore, this is actually equal, right? So now we have this variant of the earlier lemma we had proved. So consider the following. Statement. Let Ti be a family of connected subsets of X, and suppose the intersection of all these is non-empty, right? So then the union Ti is connected. Okay. So the proof of this is very similar to the proof of this lemma that we proved, this one, right? So let's just try and prove it. So suppose the union is not connected, right? Then there exists non-empty open subsets U and V such that in X, both in X, such as this union Ti is written as the disjoint union intersected with U right? Both these are non-empty, and they are of course disjoint. Open subsets in this union. Okay. So now, let we fix this element A. The idea is the same as in the earlier lemma. We fix this element A, right? So now we can intersect both sides with Ti. So this will imply that Ti is equal to Ti intersected U. Okay, so we can fix A, and before we and assume A is in this union intersection U, right? Let's assume this, right? So now we intersect this equation with Ti on both sides. So we get Ti is equal to Ti intersected U, disjoint union, Ti intersected V, right? Now this contains A and so is non-empty, right? And on the other hand, Ti is connected. This implies Ti, which forces that Ti intersection V has to be empty, right? So this implies that Ti is completely contained inside U, okay, for every I, and this happens for every I, right? So this implies that this union Ti intersected with V is empty, which is a contradiction. Right? So this intermediate lemma tells us that this union is connected when all the Ti's are connected and their intersection is non-empty. Right? So now we will apply this to our situation. So applying this to our situation, we get that xi we have written as a union of y and xi, ty. Each ty is connected, and the intersection of all these ty's, it at least contains x, right? So this implies that the intersection is not empty, because all the ty's, they contain x, right? So this implies that xi is connected. So this proves 2. Okay. And finally, let's prove 3. As x is connected, as xi is connected, this implies, so we had seen this corollary that A is connected in X implies A closure is connected. We have proved this earlier. So this implies that Xi closure is connected. Right? But by part 1, each Xi closure is contained in a unique Xj, right? But then, so thus, this Xj has to be Xi because Xi is contained in Xi closure, right? Thus, Xi closure is contained in Xi, which implies that Xi is equal to Xi closure. So this implies that Xi is closed. Okay, so this completes the proof of the proposition. So this completes the proof of the proposition. Right. So the proposition says that given any topological space X, we can break it up into these equivalence classes, and each equivalence class is defined by the relation of by that relation that we started the lecture with. Right, and each of these equivalence classes, they are connected and they are closed, and given any other connected subspace, given any connected subspace is contained in one of these equivalence classes. Right. So let's just definition. So the equivalence classes are called the connected components. Of X. Okay. So as an example, let's work this out. Right. So let Q contained in R have the subspace topology. Right. So what are the connected components? Of Q. Okay. So we claim that. Okay, so before that, note that given any A in Q, the subset singleton A is connected. Right. So the question is, what is a maximal connected subset which contains this singleton A, right? And that will be the connected component containing A. Now we claim that the connected component containing A is just this set A, right? Why is that? So basically what we are saying is, we have written Q. We can write it as a disjoint union of connected components xi. Yeah. So now choose each xi is non-empty, obviously, and just pick any A in this xi, and the claim is xi is equal to A. Right. So let's see this. Why is that? So if not, suppose B also belongs to xi and B is not equal to A. Right. So then let's assume that. So suppose that B is strictly greater than A. Right. So then we have this A is over here, B is over here, and we can choose a irrational C. Right. Choose an irrational C. Yeah, choose an irrational C, right? So then we can write xi. So C is not in Q and xi is in Q. Therefore, C is not in xi. So then xi does not contain C, right? And so we can write xi as a disjoint union of open subsets minus infinity comma C, disjoint union C comma infinity. Right? But this contradicts. Both these are non-empty because this contains A and this contains B, right? And both these are open and it's a disjoint union, right? This contradicts the connectedness of xi, right? So thus xi is forced to be a singleton, right? So thus xi is forced to be a single point. right? So therefore, all the connected components are just A in Q, right? So these are, is the decomposition of Q into connected components. Right? And let's make a remark. This is obvious. X is connected if and only if it has only one connected component. Okay, so this remark is obvious. Right? Because if X is connected, then given any 2 points X and Y, the subset T can be taken as equal to X. Right? So therefore, there will be just one equivalence class in the decomposition. And conversely, if there's just one equivalence class, then that has to be X, and therefore X is going to be connected because each equivalence class is connected. So we will end this lecture here, and in the next lecture we will introduce the topic of path connectedness. Okay.